Welcome to Module 4, Heat Transfer and Building Energy Balance. In the previous module, we used conservation of energy to test whether BAS data made physical sense. Now we are going to look at the actual paths that energy follows inside a building. The BAS does not directly command comfort. It commands equipment. It opens valves. It moves dampers. It changes fan speed. It starts pumps. But the building only responds when heat moves through air, water, walls, glass, coils, and building mass. That distinction matters in the field. When a space is too hot, the answer is not always a new set point. It may be solar gain, poor airflow, a dirty coil, air bypass, low water flow, a bad sensor, or a slow building response. In this module, we will connect conduction, convection, radiation, thermal resistance, building loads, and control loop behavior to real BAS decisions. By the end, you should be thinking less like a screen operator and more like a BAS professional who understands how the building actually exchanges heat. Before we go into the details, let us define the target for this module. You should be able to explain the three major modes of heat transfer: conduction, convection, and radiation. You should understand how R value, U value, thermal resistance, and approach temperature help us evaluate performance. You should also be able to recognize the major parts of a building load, including envelope, solar, ventilation, people, lighting, equipment, moisture, and storage. Most importantly, you should be able to connect these concepts to BAS decisions. For example, if a space is too warm, are we dealing with an airflow problem, a water flow problem, a sensor problem, solar load, envelope load, or simply thermal mass responding slowly? The goal is not to memorize equations. The goal is to use heat transfer reasoning as a field tool. Every calculation should help answer a practical question. What is happening, what evidence supports it, and what safe tests should we perform next? Let us start with the most important idea on this slide. The BAS controls equipment, but heat transfer creates a result. A valve command does not cool a space by itself. It changes water flow through a coil. A damper command does not create comfort by itself. It changes air movement and mixed air conditions. Fan and pump speed changes affect distribution, convection, and energy use. This is why two technicians can look at the same BAS screen and make very different decisions. One person sees a point value. The stronger professional asks, what physical process does this point represent? In the field, this helps prevent unnecessary work. If a cooling valve is at 100% but the leaving air temperature is still high, we do not assume the sequence is wrong. We verify chilled water temperature, flow, air volume, coil condition, bypass, valve authority, and sensor accuracy. The control command is only the request. Heat transfer is the proof that the request produced a real outcome. Heat moves in three basic ways, and most building problems involve more than one. Conduction is heat moving through a solid material. Think about heat passing through a wall, a roof, glass, pipe insulation, or a coil fin. The path, material, area, thickness, and temperature difference all matter. Convection is heat moving between a surface and a moving fluid. In BAS work, that usually means air moving across a coil, water moving through a tube, or air moving across a wall or diffuser. Radiation is heat transfer by electromagnetic waves. Solar gain through glass is the obvious example, but radiant exchange between people and surfaces also affects comfort. A room can read 72 degrees and still feel uncomfortable if the surrounding surfaces are hot or cold. In the field, identify the dominant heat transfer path before changing the sequence. If the problem is solar radiation, more aggressive airflow may help, but it may not solve the root cause. A building energy balance is a professional reality check. We choose a boundary around the building, the room, the air handler, or the coil. Then we ask what energy comes in, what energy leaves, and what is stored inside the boundary. Solar gain, outdoor air, people, lights, plug loads, and equipment can all add heat. Exhaust, envelope losses, useful heating or coolant, and stored energy all affect the balance. For a cooling coil, the air loses energy and the water gains energy. Under steady conditions, those two estimates should be reasonably close after allowing for losses and measurement uncertainty. If the water side says the coil removed a large amount of heat, but the air side says something very different, the BAS data is telling an impossible story. That does not mean the coil broke the laws of physics. It means we should question airflow, water flow, temperature sensors, humidity data, units, scaling, and operating state before making a repair decision. R value and U value are simple terms, but they have large operational consequences. R value describes resistance to heat flow. Higher R value means more resistance. U value describes how easily heat passes through an assembly. Lower U value means less heat transfer for the same area and temperature difference. The basic relationship is U equals 1 divided by total R. Then heat flow can be estimated with U times area times delta T. But here is the field warning. Real buildings are not perfect textbook assemblies. Heat may bypass insulation through framing, air can leak around openings, moisture can reduce performance. Surface films, insulation quality, and thermal bridges all affect what actually happens. So use the formula as a screening tool. It can help you estimate whether a number is reasonable. But do not confuse a simplified envelope calculation with a complete building load simulation. For BAS work, this helps us avoid blaming the sequence for problems caused by the envelope. This slide is one of the most important field lessons in the module. A fully open valve does not prove design heat transfer. A BAS graphic may show the cooling valve at 100%. That tells us what the controller is asking for. It does not prove that the valve moved correctly, that the coil has enough water, that the pump has enough differential pressure, or that the heat transfer surface is clean. Coil performance depends on the full path. Entering air and water conditions matter, flow rates matter. Surface area, fin condition, fouling, air bypass, water distribution, and valve authority all matter. This is why we do not troubleshoot only from the screen. We compare BAS data with field evidence. Is the entering water cold enough? Is leaving water warming up? Is airflow reasonable? Are the sensors trustworthy? Is the coil face dirty or bypassed? The correct question is not simply, is the coil failing? The better question is, where in the heat transfer path is performance being lost? Approach temperature gives us a useful way to evaluate heat exchangers. An approach temperature compares two temperatures that would become equal only in an ideal heat exchanger. For example, in a cooling tower, we may compare leaving condenser water to outdoor wet bulb temperature. At a coil, we may compare leaving air to entering water. At a chiller, we may compare leaving water to refrigerant temperature. A small approach often suggests effective heat transfer. A growing approach, under similar conditions, may point to fouling, reduced flow, air problems, or sensor drift. The phrase under similar conditions is critical. Approach temperature should not be compared blindly across different loads, flows, weather, or equipment states. A trend is only meaningful when the operating context is comparable. In BAS work, approach temperature can be a strong diagnostic trend. But like any trend, it must be interpreted with the system condition and measurement confidence in mind. A building load is the rate at which energy must be removed or added to maintain the target condition. That load is made from many pieces. The envelope conducts heat. Solar radiation enters through glass. Outdoor air brings sensible and latent load. Infiltration adds uncontrolled air. People, lights, plug loads, and equipment add heat. Moisture generation adds latent load. Thermal storage delays the response. This is why a BAS sequence cannot be judged only by outdoor temperature. Time of day matters. Season matters. Orientation matters. Occupancy matters. Building use matters. A data center may need cooling in winter because the equipment load is high. A perimeter office may need heat in the morning and cooling in the afternoon because solar load changes. A school may behave differently on a full occupancy day than on a holiday schedule. Good BAS decisions start by asking which load is dominant right now and whether the system is responding to the real load or only to a simple schedule. Thermal mass explains why buildings respond with delay. Air can change temperature quickly, but concrete, water, furniture, walls, equipment, and building contents store energy. They absorb heat and release it over time. This is why a morning warm-up may take longer than expected. The air may heat first, but the walls and contents are still cold. It is also why peak cooling load may occur after peak sunlight. The building absorbs solar energy first and releases it later. For BAS scheduling, this matters. A night setback may save energy in one building, but create an expensive recovery period in another. A shutdown may look good for 1 hour and create comfort complaints 2 hours later. The correct practice is to tune the BAS to the actual building response, not to clock time alone. Trends should show how long the building takes to recover, stabilize, and drift. Control stability is where heat transfer physics meets BAS tuning. A control loop should not be tuned faster than the process can respond. If the BAS changes a valve every few seconds, but the space takes 10 minutes to show a meaningful temperature change, the controller may start chasing noise instead of controlling the process. Process gain tells us how much the output changes for a given input change. Time constant tells us how quickly the process moves toward the new condition. Dead time is the delay before the response is even visible. A discharge air temperature loop can usually respond faster than a large zone temperature loop because the sensor is closer to the controlled process. A concrete building zone responds much more slowly. When tuning is too aggressive, valves hunt, dampers move constantly, actuators wear out, energy use increases, and comfort can get worse. Good tuning respects the physical speed of the system. Let us use a simple envelope heat loss example. We are given a wall U value of 0.08 BT2 per hour per square foot per degree Fahrenheit. The wall area is 5,000 square feet. Indoor temperature is 70 degrees, and outdoor temperature is 20 degrees. That gives us a 50-degree temperature difference. Using Q equals U times area times delta T, the estimate is 0.08 times 5,000 times 50, which equals 20,000 BTU per hour. The calculation is not difficult. The professional skill is explaining what the result means. This estimate excludes infiltration, thermal bridges, solar effects, moisture, adjacent spaces, and installation defects. So it is useful for screening, reasonableness, and discussion. It is not a complete load calculation. In BAS work, that distinction matters. We can use this kind of estimate to understand scale, but we should document assumptions before using it to justify a control decision. Now, let us use a cooling coil waterside calculation. The coil receives 80 gallons per minute. The water enters at 44 degrees Fahrenheit and leaves at 54 degrees Fahrenheit. The delta T is 10 degrees. Using the common water approximation, Q equals 500 times GPM times delta T. So the estimate is 500 times 80 times 10, which equals 400,000 BTU per hour. Now comes the professional judgment. If the airside calculation under steady operation says only 220,000 BTU per hour, we should not immediately blame the coil. We should investigate the evidence. Is water flow actually measured or assumed? Are the temperature sensors calibrated? Is airflow credible? Is humidity included? Is the system steady? Is there air bypass or incorrect units? This case study is a strong reminder that software is not always the root cause. The site had high heating water return temperature and poor condensing boiler performance. The first response was to lower the supply temperature reset. That sounds logical, but comfort complaints increased, and the plant still did not perform as expected. The real issue was in the physical distribution system. Several three-way valves were bypassing hot water directly back to the return. Because of that, the boilers could not see the low return water temperatures needed for good condensing operation. More aggressive software did not solve the problem because the piping and valve arrangement was working against the plant objective. The lesson is simple. Automation should not be used to hide design deficiencies. When the physical arrangement prevents a desired result, the lasting correction may require valve, piping, balancing, or mechanical changes. These common mistakes all come from the same habit, treating a displayed value or command as proof of physical performance. A 100% valve command is not proof of design heat transfer. Nameplate capacity is not proof of available capacity under current conditions. A stable air temperature is not proof that radiation or humidity are acceptable. A trend comparison is not meaningful if the loads are different. Another common mistake is tuning a loop faster than the process can respond. The controller may look active, but it may only be creating oscillation, wear, and wasted energy. Thermal mass is also often ignored. A schedule change that looks correct on paper may fail because the building stores energy and responds slowly. The field habit is this: do not use BAS commands as proof. Verify the heat transfer path with flow, temperature, load, surface condition, bypass, timing, and sensor confidence. This checklist is how we turn heat transfer theory into field practice. Before changing a sequence, sketch the heat transfer path. Identify where heat enters, where it leaves, and what stores energy. Then verify entering and leaving conditions. Confirm that flow rates are credible. Consider fouling, surface condition, air bypass, and fluid bypass. If you use approach temperature, compare it under similar load and flow. If you are adjusting schedules or tuning loops, account for thermal mass and delay. Make sure the control response matches the process speed. This checklist can save hours of unnecessary troubleshooting. It slows us down just enough to avoid guessing. In professional BAS work, the best answer is not always the fastest adjustment. The best answer is the one supported by evidence, physics, and a safe test. Let us answer the knowledge check. A cooling valve is 100% open, but the leaving air temperature is still too high. What should you do first? The best answer is C. Verify flow, entering conditions, airflow, sensor accuracy, and coil condition. Answer A. Rewriting the sequence immediately is risky because we have not proven the sequence is the problem. Answer B. Increasing pump pressure may waste energy or create noise if the real issue is sensor error, air bypass, or coil fouling. Answer D. Replacing the actuator assumes the command failed mechanically without evidence. A 100% command tells us the BAS is asking for maximum cooling. It does not prove the valve moved, that chilled water is available, that airflow is correct, or that the measurement is accurate. The professional response is to verify the physical heat transfer path before changing software or replacing parts. For the practical assignment, select one real or sample system, an air handler, coil, room, plant load, or similar piece of equipment. Your task is to build a heat transfer path diagram. Show where heat enters, where it leaves, what stores energy, and what the BAS is able to change. Then identify the measurements needed to verify that path. Do you need airflow, water flow, entering and leaving temperatures, surface temperature, humidity, outdoor conditions, valve position, damper position, or trend history? Next, state your assumptions and uncertainty. If a value is copied from design documents instead of measured, say that clearly. Finally, recommend one safe diagnostic test with acceptance criteria. The purpose is not to create a beautiful drawing. The purpose is to create a professional investigation that another technician, engineer, or manager can understand and repeat. Let us summarize Module 4. Heat moves by conduction, convection, and radiation. Envelope heat flow depends on U value, R value, area, and temperature difference. Coil performance depends on the full heat transfer path, including flow, surface condition, bypass, and valve authority. Building load changes with time, season, orientation, occupancy, and building use. We also learned that thermal mass creates delay, and that control loops must be tuned to the speed of the physical process. A fast BAS command does not mean the building can respond instantly. The main professional lesson is this: do not stop at the command. Ask what heat should be doing, what the measurements say, and whether the story is physically reasonable. In the next module, we move into psychrometrics and moist air. Temperature tells only part of the story, moisture determines the rest.